Thank you, Nova. I'll be speaking about explicit two-source extractors and resilient functions, and joint work with David Zuckerman. All right, so as we all know here in this workshop, randomness is important, and we are trying to reduce it. So it's widely used in a bunch of areas in computer science, like algorithms, cryptography, distributed computing, data structures, and many more, right? For example, in cryptography, it's actually essential that you use randomness. Well, you need that the secret keys are uniformly random, actually, because there are many easy attacks if there is some structure known about the keys that you're using in your crypto systems. Further, there is actually research which shows that for basic cryptographic tasks like bit commitment schemes and many others, you actually need uniform and uncorrelated bits. Even high entropy sources are not enough for carrying out these tasks. And there are papers which actually break such crypto systems if you just use high entropy sources. All right, so the question now is, how do you get access to these random bits? Well, there are various ways of collecting entropy from various sources. Like there are software solutions, like you use operating system interrupts, keyboard activities of users, and things like that. More sophisticated techniques require access to some physical sources of randomness. And typically what happens is these things collect some entropy, but they're far from producing uniform, purely random bits. At best, what they produce is correlated bits which contain some amount of uncertainty or entropy in them. And the task here is to use some kind of a deterministic procedure or some kind of a function to extract purely random bits out of these for all kinds of applications. For a simple example, well, could think of a stream of independent bits where each bit takes 0 with probability p and 1 with probability 1 minus p. So these kind of sources were studied by von Neumann in 1950s, and he developed a simple extractor for this. The idea is you pair bits from this stream. If it's 0, 1, you output 0. If it's 1, 0, you output 1, else you repeat. And it's fairly easy to show that he'll produce almost uniform bits using this procedure. And there have been many generalizations considered. One specific example is sources generated by constant size Markov chains. Blum gave various results on such extractors. But the question here is, how do you model a weak random source? So in the bootcamp, David gave a bunch of lectures where he motivated these things. I'll quickly go over how to model a weak source. So the first attempt could be just to use Shannon entropy. But it turns out that since in this setting you get just one sample from the source and you want to apply some function to extract bits from it, this is not strong enough. And the problematic distribution is, suppose you have a distribution D, which with very high probability always outputs a fixed string. Say it outputs the all zero string. So 0 power n is the all zero string. And with probability 0.01, it's uniform on all n bits, right? So a calculation shows that this is a distribution with linear entropy, which is very high. But if you just get one sample from it, you'll overwhelmingly always see the all zero string, and you cannot expect to extract random bits from this. So what we need actually is a stronger notion of entropy, which is a stricter notion of entropy, which is min-entropy, where for a distribution x, you look at the maximum weight it places at any point in its support. And there is a suitable normalization that you do. And an easy calculation actually shows that the min-entropy of this distribution D it's very small, it's order 1. So it's okay that we are not able to extract from such distributions. So some more intuition about min-entropy. We'll be dealing with n, k sources. So these are distributions on n bits, right? It's distributions on n bits with min-entropy at least k. What this means is that x places weight at most 2 power minus k on any input in its support. All right? And a special case is if x is uniform on some unknown subset of size 2 power k. Right? So it takes each element in this set with probability 2 power minus k. So by definition, it's an n comma k source. And this work of Shor and Goldrick, which actually shows that for most, you can show that any general n comma k source is a convex combination of these flat sources. So it's enough to deal with the special case of sources which are uniform on some unknown subset. All right, so n comma k sources are distributions on n bits with min-entropy at least k. The first definition of a randomness extractor would be a deterministic procedure that extracts, say, uniform bits from any n comma k source. So for this talk, I'll try to just focus on extracting one bit, but the general goal is to extract more bits out of it. However, it turns out that there cannot exist a single extractor for the class of all n comma n minus 1 sources. All right, so let me focus that you'd want one extractor to work for any n comma k source. You do not get to see the source and then design your extractor. You are just given a guarantee of that your source has some amount of entropy, right? And there's a lemma which shows that even if your source, the source that you start out with has entropy n minus 1, which is almost full, you cannot design a single extractor that works for all these. And it's a pretty simple exercise to show this. All right, so clearly we need more assumptions, and there have been various directions taken over the past few decades. So one is, suppose, what if your extractor now has access to more independent bits? Another direction which has been really successful is, suppose you want to extract from a source which is on n bits, but now you have a few helper seeds to extract from this. And these helper bits are uniform and independent, and it's much shorter than the n comma k source. Think of these helper seed as of size, say, order log n. Further, other directions are, suppose you have just one source, but now you have some assumptions on the source. For example, say the source is sampled by an algorithm which has limited memory, which captures many natural sources, or if it's uniform on some unknown affine subspace. Or a simpler source is, say, bit fixing sources, where it's a distribution on n bits, where you know that some unknown subset of, say, k bits are uniform and independent, and the remaining bits may or may not depend on these uniform bits. And I'll not go into this, but designing such extractors for all these classes of sources have had various applications in complexity theory, cryptography, for example, for proving lower bounds, for showing formula lower bounds as well. So it's good to design explicit extractors. That's the message from the slide. All right. So now let's go to the focus of this talk, which is two source extractors. So the setting is the following. You have, curly bracket 0, 1 power n is the set of all n bit strings. So you have two sources x, y, which are independent, and they're n comma k sources. So they are distributions on n bits, and they have min-entropy at least k, which means they place weight at most 2 power minus k on any string. And the extractor gets one sample from x, one sample from y. And again, for this talk, I'll just focus on extracting one uniform bit. But in general, the goal is to extract more bits. And more formally, what you would want is that the probability that the extractor takes value 1 when it gets sampled from x and y is close to half. And epsilon is called the error parameter of the extractor. And a simple, by now standard probabilistic method actually shows that a random function is a good two-source extractor. So a random function is a two-source extractor for sources with min-entropy as small as log n plus order 1. Right? So it's a source on n bits, but it has entropy just log n. And the most naive way of going through all functions would take doubly exponential time to find such a function. And in computer science, if you want to efficiently do things, you want polytime algorithm. This question of explicitly constructing two source extractors was raised in the 80s, and so the constructions known was the first work by Shor and Goldrick gave an extractor which works when both the sources x and y have min-entropy slightly larger than n/2. Bourgain slightly improved the situation after 20 years using sophisticated methods from additive combinatorics and got it down to 0.5 minus alpha times n, where alpha is a very small universal constant. And Randomness showed how to extract when one of the sources has entropy slightly larger than n/2, and the other source is, it can have very small min-entropy, like order log n.
And this is for extracting one bit of, or?
No, all of these extracts almost all of the min-entropy out of the source.
Oh, okay.
Yeah. All right. And it remained a challenging open problem to get an extractor where both the sources have min-entropy much smaller than, say, n/2, even 0.1 n. So the main result with David in this talk is an explicit two-source extractor, which works for min-entropy polylog n, where the C in our work was 75. And the running time is poly n/epsilon. So the ideal running time that you would want is poly n and log 1/epsilon. So that's one open problem which I would encourage people to work on in this workshop. All right. There's a very nice matrix way of viewing two-source extractor. In particular, it's a truth table of the two-source extractor. So, so this is the truth table. You think of the rows as the row index as the input of the first source, input from the first source, the column index as the input from the second source. So there are 2 power n rows, 2 power n columns corresponding to each n-bit string. And the entry corresponding to it is the output of the extractor, right? So, by the property that it's a two-source extractor, if you look at any 2 power k columns and 2 power k rows, then the corresponding submatrix that you get roughly has equal number of zeros and ones. So it's a low discrepancy Boolean matrix, and such matrices have applications in communication complexity and other areas in computer science. Also, there is a nice graph theoretic way of viewing a two-source extractor which gives important objects in extremal combinatorics called Ramsey graphs. A k-Ramsey graph is on n vertices, and it does not have any independent set or clique of size k. And the bipartite version is that it doesn't have the complete or empty k cross k subgraph. In 1928, Ramsey showed that there does not exist a log n/2 Ramsey graph on n vertices. And almost matching this, Edish using the probabilistic method showed that there exists 2 log n Ramsey graphs on n vertices. And he posed it as challenging open problem to actually explicitly construct such Ramsey graphs. So given a two-source extractor, how do we come up with a Ramsey graph? Well, it's very easy. What you do is you have 2 power n nodes on the left, 2 power n nodes on the right. So each node on the left corresponds to an n-bit string, similarly on the right. And you think of the input from the first source as a node on the left, input from the second source as a node on the right. And given your two-source extractor, if it's the complete graph, you color all the edges on which the extractor outputs 1 to green. All the edges on which the extractor outputs 0 to red. And the guarantee is that if you look at 2 power k vertices on the left, 2 power k vertices on the right, then roughly there are equal number of red edges and green edges. That's directly from the extractor property. So, and this gives you a bipartite Ramsey graph. All right, and there has been a long line of work for the last 70 years on constructing explicit Ramsey graphs. I'll not go over all the details, but there was some work a lot of work was stuck at this bound of, so the probabilistic bound is 2 log n. There's a lot of work which got stuck at 2 power square root log n. Then seminal works of Barak et al. Got an exponential improvement. And our work implies another exponential improvement, and it gets to 2 power log n power c for some constant c. So if c is 1, in fact, you get the Edish's probabilistic bound. And independent work of Gil Cohen on two-source dispersers also implies Ramsey graphs. So he independently achieved the same results on Ramsey graphs. All right. let's come back to actually constructing two source extractors now.
Is there any lower bound for K? In the case of Ramsey, you have the lower bound for
of log n over 2, yeah.
Yeah, but in this case, what is the lower?
It's the same. Yeah. A constant of
maybe it's log n
log n.
instead of over 2.
Right. Okay, so ingredients are seeded extractors, which you have already, some of you have seen in the bootcamp. Slightly fancier extractors called non-malleable extractors, resilient functions, and we'll look at some kind of sources. All right, so, and the outline of the construction is the following, that using some extractor machinery, we'll convert, given a sample from X and Y, we'll transform it into a single source, which has these white coordinates, which are good, they're independent, slightly lying, they're independent random bits, and red coordinates, which actually depend on these bits. And then we'll use some other machinery and some other pseudorandomness tools to get a uniform bit. All right, so let's start out with the ingredients. A seeded extractor takes as input weak source X, which is an n comma k source, and some independent helper bits, D, where D is short, much shorter than n. And what you'd want is that the output of the extractor is uniform. And not just this, but you'd want the output of the extractor to be uniform, even conditioned on the seed. So even given the seed, the output should look uniform. So one could say that since Y is already uniform, the extractor could just output Y. So you don't want the extractor to cheat. So that's kind of an informal way of saying this. And by a really beautiful line of work, we have seeded extractors which achieve almost optimal parameters. So you can extract using just log n bits, and you get almost all of the min-entropy out of your source, right? And an equivalent way of presenting these seeded extractors is the following. So what you do is you fix the seed of the extractor. So now fixing the seed to Y, the extractor is now just the function of the source X. Right? So there are 2 power d functions corresponding to each fixing of the seed. And the property of the strong seeded extractor is the following, that there exists a large fraction of seeds, namely 1 minus epsilon fraction of the seeds, such that for any such fixing, if you apply the corresponding function on your source X, the output that you get, output distribution that you get, is almost close to uniform in statistical distance. So we'll always be dealing with statistical distance in this talk. All right. And next we'll need a slightly fancier extractor. It's called a non-malleable extractor, which was introduced by Doris and Wicks in cryptography, but I'll not present the original definition. I'll present something which is enough for this talk, and it's also equivalent. So it's called a t-Non-Malleable extractor. And again, it takes a weak source X, and it takes a seed, and it outputs 1 bit. For this talk, we'll just output 1 bit. And the property is that, again, there's a large fraction of seeds, such that now if you pick any t distinct seeds from this set, and look at the corresponding functions, Fy, and you apply Fy on the source X, then you'd want these to be independent and uniform. Right? So the joint distribution of Fy1 of X through Fyt of X is actually close to uniform. Right? So when t is 1, this is exactly a strong seeded extractor. Right? Right. And it's turned out that it's tricky to construct these things. And so in joint work with Vipul Goyal and Shinley, we constructed these extractors, which has seed length, which is poly in T and poly log n, and also similar entropy, and gets almost all of the things out. And there has been a lot of work in getting the poly factors right after this. So, all right. Yes, please.
Can you also with extractors, if you use like the probabilistic method, you can see how well a random extractor would do. How does these bounds compare with?
So, right. So for the seeded extractor, it's pretty. So you'd want seed which is log n plus log 1 over epsilon up to constants. And even here, the dependence on epsilon is log 1 over epsilon, and for t, you can show that the seed length depends logarithmically on t. And the min entropy is, you need to have order, like, this thing is off by 2. But now the best known is, I think, log n times log n. So, and the final ingredient that we'll need is resilient functions. So the best way to motivate this is through this coin flipping game. So it was introduced by Benor and Linil. And suppose you have a bunch of n players who are flipping coins and sending it to a trusted authority who applies a function f to output a bit b, where all of the players are convinced that it's an unbiased bit. So if everyone is playing honestly and they send uniform bits, f could just pick one of the players or apply parity. It could basically do anything. But the setting is much more interesting when there are malicious coalitions of players. So these coalitions actually wait for the other players to send their bits, and then looking at them, they send their own bits, right? And how do you measure the influence of this coalition? Well, you say that it's the probability over the coin flips of the honest players that the coalition Q can actually change the value of the function f, right? Okay. So more formally now, a resilient function is a Boolean function from n bits to 1 bit. And let Q be a subset of coordinates. And you sample a string x in the following way, that you sample bits outside Q uniformly and independently and leave the bits in Q unfixed. And then you look at the function f of x, which is now just a function of the coordinates in Q, that it's not the constant function. Or in other words, the bits in Q can actually change the value of the function. So this is exactly the influence of Q on the function f. And a Q, epsilon resilient function is a function such that no set of Q coordinates can have influence more than epsilon on the function f. So a trivial resilient function is just the constant function, because any set of coordinates cannot change the value of the function. So we'll be focused on constructing resilient functions which have bias close to 1/2, or its expectation under the uniform distribution is close to 1/2. And for examples, well, parity is not a good resilient function because even one coordinate can change its value, and majority can handle up to square root n bad players. Great. And resilient functions are extractors for certain kind of sources. So we'll be interested in non-oblivious bit fixing sources, NOBF sources. So here, the white bits correspond to good bits, and they're sampled from some distribution D, which you can even think of as uniform and independent. And the red bits, they arbitrarily depend on the values of the white bits. And if you have a function f which is Q, D, epsilon resilient, and it's also unbiased on the distribution D, then it's easy to see that the probability f of x is 1 is close to 1/2. And this is because since its bias is 1/2, and the bits in the red coordinates can at most change the value with probability epsilon, it can bias the value of the function f of x by at most epsilon. So f is an extractor for all such sources. All right, so back to our program. Let's try to execute this step.
Sure. What does NOBF stand for again?
Non-oblivious. So it's a bit fixing source, and the red coordinates actually depend on the value of the white coordinates, so it's not oblivious, it's non-oblivious. All right, so a preliminary attempt. Suppose we just get a good strong-seeded extractor. So recall that for a strong-seeded extractor, it takes, so let X be the first source to the two-source extractor, right? It gets a sample. And the idea is run over all the seeds of the extractor. Well, since we have really good constructions of strong-seeded extractors where D is order log n, the total number of seeds is poly n, right? So just run over all the seeds, and so corresponding to each seed, since the extractor just outputs 1 bit, the ith coordinate of this long string corresponds to the extractor run on the ith seed, right? It gets one sample from X and runs over all the seeds, right? So you brute force over all the seeds. It's important that you do not get a uniform seed. You brute force over all the seeds. And the property that we saw of strong seeded extractors is that the output is close to uniform for most seeds, right? So for 1 minus epsilon fraction of this string, they're uniform bits, almost uniform bits. And the red bits are not uniform, and they arbitrarily depend on these white bits as well. So it seems like we're pretty close to maybe extracting bits because there are a lot of uniform bits there. So maybe taking the majority of these bits could give you a uniform bit. But it does not work because the uniform bits, they're uniform on their own, but they may be arbitrarily correlated. You do not know what's going on there. So it's not clear why majority should work here. A second attempt is to get more structure in those uniform bits, to make them almost t-wise independent. And the tool for this, seeing the definition of a t-Non-Malleable extractor, is just that. Now take a non-malleable extractor, get a sample from X, and run the non-malleable extractor on all its seeds, right? Now, the length of this string is actually quasi-poly. But say we don't care. Maybe we are happy with just a two-source extractor which works in quasi-poly time. So we brute force over all these seeds. And now you know that these white bits, they're all almost t-wise independent, right? There's a lot of structure in them. And the red bits, there are at most epsilon fraction of them, and they arbitrarily depend on the white bits. Yeah.
How do we know that it's an epsilon fraction? Don't we just know that it's like an epsilon fraction of t tuples that are bad?
No, so you can actually prove, it's fairly simple to show that there's actually, so the way I defined it was that there's this set of 1 minus epsilon fraction of seeds, such that if you pick any t distinct tuples from there, right, so you can actually. Yeah. All right, so now one could probably apply majority and use de-randomized central limit theorem to probably try to get random bits out of this. But the problem is that there are just too many faulty bits. So epsilon times d, which is the fraction of bad bits, is much greater than square root d, which is roughly what you get from the central limit theorem. But actually, you could replace majority with more resilient functions to get over this. But the real problem is that these white bits, they're almost t-wise independent. And if you go to a t-wise independent distribution, you add too much error. So anything which is greater than 1 is meaningless here. So this thing doesn't work. And it's good that it doesn't work because till now we have just used one source. So, and we know that there cannot exist a one source extractor. Good. So the idea is now to use the second source to compress the string. And the way to compress it is to project it to a pseudorandom set of coordinates. And this by now is standard in the extractor literature, is to use a sampler. Unfortunately, we just have another weak source y, which we haven't used so far. But it's known, by work of David Zuckerman, we actually know how to sample using weak sources. So the idea is you take a seeded extractor whose output would actually, each output would correspond to a coordinate in the string, right? So y is now the second source which finally appears. Take a strong seeded extractor, run it over all its seeds. So now note that m, since a seeded extractor's seed length is order log n, the number of seeds is poly n. So you run over all its seeds, and corresponding to the output of each seed, we get an index of a coordinate in this long string, right? So throw away all the other coordinates. Now we are left with a projection which is just poly n in size. And note that actually the ith bit in this is the non-malleable extractor on X with the seed as extractor of y comma ri, right? So to get the string, you don't actually have to run all the non-malleable extractor. All you got to do is use the seeded extractor with the second source to choose the seeds and then run the non-malleable extractor on it. Right. So now we end up with a source which is poly n in size. And the number of faulty bits with calculation you can show is little of m. So it's actually m per 0.99. Right, for some delta. And why is this the case? Well, because now on a very informal level, what you have done is the length m no longer depends on the error epsilon, which was from the non-malleable extractor. So you can push epsilon down and get this to the right fraction. Great. So now, after all this, we can essentially forget we had two sources and just focus on extracting from this source, which we have developed now. So let's go to the second part of the construction. All right. So fresh start. You have a string z on n bits. The white bits, they are sampled from a t-wise independent distribution. So if you look at any t coordinates and project them, then they're almost independent and uniform. So t is polylog n. The number of red bits is n power 0.99. And these red bits arbitrarily depend on the values of the white bits. Right? And we have seen that this is exactly the kind of sources for which resilient functions are extractors. Right? So, and the resilient function that we'll construct will be a low depth circuit.
So Eshan, can you comment in which step? Was it the previous step, this counting step, where the error has to be one of a polynomial? That's the step, the counting step that you can push epsilon down, or
right.
Where is it, which step kind of?
You mean here the calculation?
Right.
Yeah.
Is it this step which restricts the error to be inverse polynomial? So which step here? I mean, which is a critical step where inverse polynomial cannot?
Right. So the non-malleable extractor can have. So the major bottleneck is using the resilient function, which is the second step, because there, just KKL, or it shows that you cannot go below the length of the string. And since we are working with strings of polylength, you cannot have less than one.
So but even here it's like, I guess, m is n divided by epsilon prime, and I guess it means that epsilon prime cannot be like exponential or exponentially low, right? I mean, even here it looks like you should set it in
Yeah.
polynomial.
Right. So, yeah, exactly. Yeah, you cannot have epsilon prime, which is too small. Okay. So now you're trying to extract from these kind of sources where these bits are t-wise independent. And the first step that we'll do here is translate into a slightly easier problem where we'll say that these white bits, instead of being t-wise independent, they're actually uniform. So this is a big step because there are n minus little of n white bits, and they were only polylog-wise independent before. But we are saying it's enough to solve the problem when they're uniform. And this step is through a easy but neat observation which says that if the resilient function is of a certain kind, then you can actually solve just this problem and reduce it to the other problem. So the idea is this, that suppose the resilient function is actually monotone. Then you can actually check if the good bits, after sampling the good bits, the function's value, the value of the resilient function is already fixed or not. Right? And the way to do it is set all the bits in the coalition Q to zeros, all the bits in the coalition Q to ones, and check if they're the same output. Now, since C is a monotone function, if at all the coordinates in Q could actually change the value of the function, then these both have to be different, right? Because it's monotone. And note that if C is a low depth circuit, then C prime is also a low depth circuit. Right? So what we have seen is that the probability that Q can actually change the value when the white bits are sampled from some distribution D is exactly the expected value of this circuit C prime that we constructed with the not equals thing. Right? So now the idea is to invoke the seminal result of Braverman on small depth circuits, which says that t-wise independence fools low depth circuits, or in other sense, it cannot distinguish between uniform and t-wise independence. So what it essentially says is that if C prime is a low depth circuit, then the expected value of C prime under a t-wise independent distribution is pretty close to when the good bits are sampled from a uniform distribution, right? So this translates into saying that the influence that a coalition has when the good bits are t-wise independent is close to the influence it has when the good bits are uniform. So this is the reduction.
Both monotonicity and AC0, so you need like both
low depth and monotonicity. And for getting hold of such functions, it turns out that Itay lineal got us pretty close, but there are some problems. So Itay lineal constructed a probabilistic construction of low depth circuits. So their construction was roughly this, that they took a tribe function. So a tribe is OR of ANDs on disjoint sets of variables. So each is a block. If a block unanimously says 1, then the tribe function is 1. And corresponding to how you partition these n coordinates, you get different tribes. So what the ideal linear function looks like this, that it randomly partitions, it takes n random partitions, and corresponding to them looks at the tribes function that you get. They also randomly negate variables, and then take an AND of all these tribe functions. So it's a probabilistic construction, that's a problem. And it's also not monotone. But the good thing is that they show that there exist functions in this probabilistic space which are resilient to coalitions of size n over log square n. So we need just resilience up to n power 0.99, but this is even beyond that. So the problems.
Where is non-monotonicity? I mean, what you drew is monotone, but I guess there are negations. So
yeah. So yeah.
Negated, I see.
Yeah. So the naive de-randomization of going through all partitions and all negations would take n over order n squared time, and further it's not monotone. So our main contribution here is to de-randomize ith-lineal and also remove the monotonicity things. And the key ingredient, at least one of the key ingredients, is coming up with a pseudo-random collection of partitions, because each partition gives you a tribes function. So the properties that we roughly need from the partition are that, so we have a bunch of partitions, n partitions say, and we need that for any small subset. So for any 0.99 set of coordinates, it has to have small intersection with most partitions. And by intersection with the partition, I mean intersection with each block of the partition. So any small subset should have small intersection with each block of the partition, and we need a lot of such partitions. And this is used to bound the influence of exactly this set of coordinates. And further, we also need a design kind of property that the partition should be, so if you look at any block of a partition and any other block of any other partition, then they should have limited intersection. So it's kind of a design property, and this is actually used to show that the function that we construct has bias close to half under the uniform distribution, which turns out to be tricky. And the way we construct these partitions is again using seeded extractors. So roughly, recall that seeded extractors are samplers. So if you look at the graph of a seeded extractor, that is, the weak source input corresponds to the left node. The output of the seeded extractor is on the right. And there is an edge between them if some seed takes the input to the output. And we call an input x bad with respect to a set T, statistical test T, if the neighbors overhit this set T. And it was shown by Zuckerman that the number of such x's is bounded by 2 power k, where k is the entropy for which the extractor works. So it somehow is related to the first property, where we do not want too many things to have large intersection with a small set. But it's far from trivial to see how this can be used to get partitions. So this slide is a very generic statement about how to, get partitions from a slightly simpler problem.
What are the parameters in the partitions? What is the size of each part? And what?
So the block length is like log n.
So it's the same. I see.
Yeah. Yeah. So suppose you want to partition n, and say n is m times b, where say b is like log n. And suppose you have a collection of sets S1 through SR, such that they're small sets, they're log n size sets. And each SI looks like 1, I1 through B, IB, where I1 through IB are numbers from 1 to m. Right? So the claim is that using each SI, you can actually come up with a partition. And the way to do it is this, that think of SI as a line here, right? And by shifting this line, looking at all the shifts, you cover this space of n, right? So each SI defines a partition, and then you get R partition. So if you want to partition n, if you want a lot of partitions of n, one way is to come up with these small sets and then shift them. And the way we come up with these small sets is looking at the graph of the seeded extractor. And corresponding to each left node, we define the neighbor to be the SIs. So this gives you our partitions. And the properties that we needed from the partitions translates to properties of this graph. The first property is the limited intersection property, which is fairly direct from the sampler view of the extractor. The second is a design property, which Luca-Trevisan's extractor actually satisfies. We proved this. So using these things, we come up with the partitions. And so the main ingredients are the pseudorandom partitions. We show a new way of analyzing the bias of the anti-linear function, which is actually crucial in showing that you don't need to negate variables, and you get a monotone function. All right, so applying these things, on this source, you get the uniform bit. Well, there has been a lot of subsequent work with a lot of new ideas, old techniques, which gets the Min-Entropy requirement. So ours was log power 75, and this now the best work is some constant times log n times log n. Shin showed how to extract more bits. There's been exciting progress on a lot of different other kinds of sources which were stuck for some time. Raghu improved our resilient function, Raghu Meka. And one problem which would be really nice to solve is achieving small error.
Thank you. Questions?
I have a question. Yeah, I wanted to ask. What was it again? Yeah, I think you mentioned that simply assume. In the beginning, you mentioned how simply assuming. Wait. Actually, wait. Actually, wait. No, I can't remember what I was going to ask. Sorry.
Okay, so let's thank Eshan again. We have a 15 minutes break.